Hello everybody, I'm Pooya, and in this presentation I'm going to talk about a new approach in the area of incremental weighted erasable pattern mining presented in a paper by the title of Incremental Weighted Erasable Pattern Mining with List Structure, published in January 2020 by Leung et al. We first start with getting familiar with the definition of data mining and then the concept of erasable pattern mining. As we learned in the class, data mining is defined as a non-trivial extraction of previously unknown and potentially useful information from data. As for the pattern mining, we should first state that as the size of data becoming bigger, data mining techniques which find interesting knowledge in this huge amount of information are getting more important and attracting more attention. One of the techniques of data mining that extracts useful pattern information for databases, usually large databases, is called pattern mining. By pattern, we mean either frequent item sets, associations, subgraphs, sequential rules, or periodic patterns. As we became familiar with a priori and FP rows, our two representatives are pattern mining algorithm. We saw that a priori is based on breadth first search and scans the database several times to find frequent patterns. On the other hand, FP rows is based on depth first search and scans the database twice while using a divide and conquer method. Usually in pattern mining, we use methods that use a minimum threshold to extract meaningful patterns which are greater than a user-specified threshold, like when we are looking for patterns with frequency greater than a given threshold. However, in erasable pattern mining, we are looking for patterns with profit value of less than a maximum threshold specified by the user. And the patterns extracted are called erasable patterns. As an example, consider a factory producing a large collect of products, and have in mind that each product is made up of a few components. Obviously, for manufacturing the products, the factory should purchase and store these components. Now, suppose that a financial crisis is happening, and a vital question here is how to plan the manufacture of products with limited money. Obviously, the factory must stop manufacturing some products, but the loss of the factory's profit caused by stopping manufacturing some products should be somehow controllable. In other words, the company must produce only profitable products and remove the components included in products with low profits. In this case, different possible sets of these kinds of components called erasable item sets. In the simplest setting, erasable pattern mining, or even regular pattern mining, is applied on fixed databases. However, since the data generated in real world is dynamic, it is an important issue to deal with incremental databases as well. In an incremental environment, new data can be added to existing database, and the techniques must scan the newly inserted data only once and reflect the new information in the previously constructed data structure. As a result, faster techniques are needed to extract meaningful patterns from real-world situations. To deal with incremental databases and solve the mentioned limitations, different approaches have been proposed, such as sliding window-based models and landmark window-based models, which we saw in the class as well. Another aspect of data is if it's weighted or not. Real-world data is often characterized such that each item has a different importance, for example, in terms of price, rarity, or quantity. This is while traditional pattern mining techniques usually treat different data and items all times with the same importance, and thus it is not suitable for mining real-world data. So having methods which can handle the importance of items differently is of our interest. Now we are familiar with all basic concepts to talk about the contribution of this paper. In this paper, a new efficient algorithm in the field of pattern mining is proposed. The main goal of it is to deal with the incremental databases and extract the erasable pattern while considering weighted condition. To do so, it uses a list structure, as we will see in the remaining slides. This algorithm is called IWEL, which stands for Incremental Weighted Erasable Pattern Mining Based List. In this part, I'm going to describe how IWEL algorithm works. The database the algorithm deals with is as simple as the following table. Each record of the database is representing a product, and each product has a unique product ID, PID. Each product consists of some items which are the components needed to produce that specific product. For example, the components of product P1 are A and G. And finally, each product has a given profit value, which representing the profit we gain by producing it. In this application, a pattern X is defined as a subset of the domain item sets. For example, set of A is a pattern of size 1, and the set of BGH is a pattern of size 3. Now we first define some concepts. The first one is gain of a pattern. The gain of a pattern X is the sum of the profit values of all products containing at least one of the items of X. For example, because item A is included in products P1, P4, and P5, as you can see in the picture, the gain of A is equal to 900, the profit of product P1, plus 300, the profit of P4, plus 200, the profit of P5, sum up to 1400. As another example, the gain of the pattern AH is 2100 because the items A or H is included in P1, P2, P4, and P5. So its gain is equal to 900 plus 700 plus 300 plus 200, sum up to 2100. Intuitively, it means that if we remove the components A and H, or pattern X, because we couldn't produce the products P1, P2, P4, and P5 anymore, as a result, we will lose a total profit of 2100. Another concept is the maximum gain threshold. First, let delta be a user-given percentage value threshold. The maximum gain threshold, or MGT, is obtained by multiplying delta by the total profit value of all products. For example, if delta is chosen to be 60%, MGT, or the maximum threshold, is equal to 3900, which is the sum of all profit values multiplied by 0.6, which gives us 2340 as the final value of MGT. In fact, here we want to lose at most 60% of the whole profit after removing some components from production line. If the problem is as simple as we already talked about, we can say that if the gain of X, or pattern X, is less than or equal to maximum threshold, then pattern X is an erasable pattern. For example, with delta equal to 60%, we saw that maximum threshold will be 2340 because the gain of pattern AH was 2100. AH is an erasable pattern as 2100 is less than or equal to MGT. More precisely, this means we can not purchase components A and H anymore. Although we cannot manufacture any more products 1, 2, and 5 due to the lack of A and H, the loss of the gain caused by these products is so-called controllable, meaning it's less than 60% of the total gain of the factory. But what if the items are weighted? For example, suppose that whatever the weight of an item is higher, it plays a more important role in producing the product, including it. Here on the left, you can see the given weights for the domain items, where the weights are normalized to be greater than 0 and less than 1. To deal with the weighted items, the authors actually introduce some more concepts. The first one is contribution of an item in a product or transaction. The contribution of an item I in a transaction P, denoted by C of I and P, is the weight of I divided by the total weight of all items in P. For example, the contribution of item A in product P1 is equal to the weight of A divided by the sum of weights of all items in product P1, meaning items A and G. So the contribution of A in P1 is 0.5. As another example, the contribution of item A in product P4 is equal to the weight of A divided by the sum of the weights of all items in product P4, meaning items A, C, E, H, and I. As a result, the contribution of A in P4 is 0.3. Likewise, we can calculate the contribution of A in product P5. Note that the contribution of A is not defined in products P2, P3, and P6 because they do not include item A. So we can calculate the contribution of other items in each of the products, including them. Here, the pound signs are representing some value for each entry. Now we can define another concept called the average weight of an item. The average weight of an item I, denoted by AW of I, is the average of the contribution of I over all transactions containing I. For example, the average weight of item A is equal to the average of the contribution of A in products P1, P2, and P3, which is, P1, P4, and P5, which is equal to 0.35. Intuitively, this value is representing the average importance of item A over all products which A is included in. We can calculate the average weight of other items in the same way, meaning items B, C, all the way to I. The average weight can also be defined for a pattern. The average weight of a pattern X, which is denoted by AW of X, is the average of the average contribution values, meaning AW values of the items included in X. For example, the average weight of pattern AH is the average of the AW of item A, which is 0.35, and the AW of item H, which is 0.23. The final value is equal to 0.29. Now we are ready to define a final concept which we can use to distinguish erasable patterns. This value is called the weighted gain of a pattern. The weighted gain of a pattern X, denoted by W gain of X, is a value obtained by dividing the gain of X by the average weight of X. Let's first see an example for calculating it, and then we will discuss what this value really means. For example, the weighted gain of AH is equal to the gain of AH divided by the AW of AH. We already calculated the value of the gain of AH, which was the total profit of products including A or H, as well as we calculated the value of AW of A and H, which was the average of AWs of items A and H. So the final value for W gain of AH will be equal to 2100 divided by 0.29, which is equal to 7241. Through the equation of weighted gain of x, we can conclude that if weighted gain of x value is relatively high, the products including x have a high profit, but x is not a big part of or important part of the corresponding products. On the other hand, if W gain of x is relatively low, it means that products containing x have a low profit in total, but X plays an important role in manufacturing these products. That's why the authors claim that this is actually a calculation method suitable for erasable pattern mining with weighted condition. To have a better idea about this value, consider two patterns which have the same gain values. We probably prefer not to remove the pattern that doesn't play an important part in producing the products including it. In other words, we do not like to stop producing some products due to the lack of some unimportant components of them. So the authors define a weighted erasable pattern as follows. If the weighted gain of x is not greater than the maximum threshold, or MGT, pattern x is a weighted erasable pattern. For example, with delta equal to 60%, the maximum gain threshold will be 2340. We also saw that weighted gain of pattern A and H is equal to 7241. As a result, we can say that pattern AH is not an erasable pattern because 7241 is not less than or equal to maximum threshold value. This is why we saw that without considering weights, the pattern AH was an erasable pattern with the same threshold. Now let's see what we need to store after a database scan to implement this idea efficiently, as well as to be able to extend the idea to deal with incremental databases. In fact, after one scan of database, we only store 3 lists. The first list stores the production ID of each product together with its profit value. The second list stores the average weight value of each of the items using the contribution values. And the final list stores a list of the product IDs that each item is included in. For example, for item A, we only store the IDs P1, P4, and P5 because only these products include item A. So all we have after reading the database once is the following lists. In fact, using these lists, we have AW values and we can calculate the gain values of any pattern by combining two lists of profits and contributions. So we will be able to calculate the weight gain value of any possible pattern and then compare it with the maximum threshold to check if it's an erasable pattern or not. Now we want to see how to deal with the incremental databases using the introduced structures and concepts. Suppose the first 6 transactions here are the original database. The next 2 transactions are the first incremental database called IDB1, and the remaining 2 transactions are the second incremental database called IDB2. Note that after being inserted the entire of each database, user can request a mining or request an insertion of a new database. So it means that after inserting each database, the algorithm should be prepared to start a mining process. The algorithm first gets the original database. When the original database is added, the algorithm constructs corresponding tree lists for all products of it as follows. Now suppose that the request of user after inserting the original database is an insertion of a new database, meaning the second database IDB1. When the first incremental database IDB1 is added, first the profit and contribution lists are updated. Actually, 2 new items are added to profit list, and the contribution of the items existing in new products will be updated too. Because the contribution of items A, E, F, and I in different products are now changed, we should recalculate their corresponding AW values. For example, the AW value of A was previously an average value over 3 products P1, P4, and P5, but now it should be recalculated over 4 products because it is now present in P8 as well. When we update tree lists, we are done with first 2 databases. Now again, user can request a mining over these 2 databases or request an insertion of a new database. Suppose the user wants to insert IDB2 as well. So similar to adding IDB1, the second incremental database IDB2 is added, and again the profit and contribute lists are updated. Because the contribution of items B, D, and H in different products are now changed, we should recalculate their corresponding AW values as well. And now we are done with 3 databases. This time, suppose that the user requests to mine and extract weighted erasable patterns. User provides the threshold value equal to 40%, because the total profit of all products now is 16,900. The maximum gain threshold will be 16,900 multiplied by 0.4 equal to 2560. To extract erasable patterns, one solution is to consider every possible pattern X, then calculate the weight gain value of X, and finally compare it with the maximum threshold. So we can first form all patterns of one item, as you can see in the table on the right. For example, here the pattern C is not an erasable pattern because its weighted gain value is greater than the maximum threshold. Then we should form all patterns of 2 items using the domain items. For example, here's the pattern CF is an erasable pattern because its weighted gain value is less than the maximum threshold. But one question is that can we prune some patterns during this process? We already know that some erasable pattern mining techniques satisfies anti-monotone property. As you might know, it means that if pattern X is not valid or is not erasable here, then all super patterns or supersets of X are also invalid. As a result, using this attribute, some unnecessary operation can be eliminated in advance without pattern loss. However, the constraint, if weighted gain of X is less than or equal to maximum threshold or not, which we use to find erasable patterns, may violate the anti-monotone property. For example, as we saw in the previous example, pattern C was not an erasable pattern. However, CF, which is a superset of C, was an erasable pattern. This is because of the fact that in the calculation of weighted gain of X, although the value of gain of X continues to increase when forming supersets of pattern X, average weight of X or AW of X may decrease or increase as it is an average value over items included in X. But to solve this problem, the author suggests an alternative value called the maximum weighted gain, which can be used instead of weighted gain value. The maximum weighted gain of a pattern X, denoted by M gain of X, is calculated by gain of X divided by the largest AW value of one-legs patterns, which is a fixed value for all patterns. For example, as we saw previously, after inserting first two databases, we have the following average weight values for one-length patterns. As a result, the maximum AW is the maximum of these numbers you can see here, which is 1. So MAW is 1 here. It is proved that maximum gain of X is always less than or equal to weighted gain of X. It means that we can use maximum gain of X to produce candidates for erasable patterns while pruning some patterns because of its anti-monotone property. Then we can check the final candidates with their real weighted gain or W gain to find the real weighted erasable patterns. Let's see the process using an example. Unlike our previous example, suppose this time we are going to mine and extract weighted erasable patterns after inserting two first databases, and the threshold parameter delta is set to be 35%. When the second database, meaning IDB1, is inserted into data structure and the three lists are updated, the sum of all product profits is 4,700. So with delta equal to 35%, we have the maximum threshold equal to 1645. Besides, the maximum of AW values is AW value of F here, which is 1. As a result, MAW value will be 1 as well. Now we start the process of mining the erasable patterns by forming the one-length candidates and calculate the maximum gain for each of them. Then check if they are less than the maximum threshold or not. You can see the calculated values here, the calculated values for maximum gain of each pattern in the table on the right. Here we can say that because maximum gain of pattern A, D, and G are greater than the maximum threshold, which is 1645, they cannot be erasable patterns. As a result, and because of the anti-monotone property of maximum gain, their supersets cannot be erasable patterns as well. So we won't consider them anymore and only form two length patterns including items B, C, E, F, H, and I. In the table on the right here, you can find all possible two length items sets including two of these items. Again, we only consider two length patterns with maximum gain less than or equal to MGT to form three length item sets. As you can see, many of them this time get pruned. Similar to what we do in a priori algorithm to create new candidates, we consider each two patterns of length 2 that have the common item in their first place. For example, consider patterns BF and BH with the common item in their first places. Then we form a three length pattern, meaning BFH. Before adding it to three length candidates, we apply the pruning step, which is checking if all possible two length subsets of it are valid patterns in previous two length candidate table or not. Here, because BF and BH and FH are all valid patterns, we will add the pattern BFH to three length candidate table as a new candidate. Doing the similar process for all possible candidates, we reach the final three length candidate table on the right. Because their two first items are not common, we won't have any four length candidate. So we are done with generating the candidates here. As the last step of the process, now each candidate pattern should be checked with its real weighted gain value. For example, for one length candidates, we have the weighted gain values showed by green, and among them, in this case, as we can see, only the gain value of the patterns F is less than the maximum gain threshold, which was 1645. So it is the only weighted erasable pattern of length 1. We repeat the same process for the final candidates of length 2 or more as well to find all final erasable patterns. We are done with the algorithm, and to test the efficiency of the proposed algorithm, the authors actually have done different evaluations. Here we will take a look at some of them. The authors actually compare IWEL algorithm with three previously proposed erasable pattern mining methods called Line, which is a list-based algorithm and proposed in 2018, IWEI, a tree-based algorithm proposed in 2016, and ID Merit Plus, which is another algorithm in this field and proposed in 2013. Actually, they use various real data sets and synthetic data sets. The real data sets, which are widely used for performance evaluation in the pattern mining area, are as follows: Accidents Connect, PUMSB, Mushroom, Retail, WebView, and BMS-POS. Some of these datasets, like Accident Connect, PUMSB, and Mushroom, are dense datasets, while others, meaning Retail, WebView, and BMS, can be considered as sparse datasets, meaning the average number of items in each of their transactions is relatively low. To prepare these datasets, because these datasets do not have their own profit values, the authors randomly set the profits. In addition, they assign weighting conditions for the items in each data field. Here we see the results of the runtime test on 4 dense datasets. The x-axis here is representing the different thresholds, and the y-axis is the running time of the algorithm in seconds. IWEL algorithm is shown by a light blue color here or here. As you can see, it shows the best performance for all cases. As another evaluation, here we see the results for memory usage tests on 4 different dense datasets again. Here again, the x-axis is representing the different thresholds, and the y-axis is here the memory that each of the algorithms used to complete their tasks. One fact to notice is that when the threshold value increases, the memory usage of all algorithms is almost constant. The reason is that each algorithm extracts patterns but doesn't store them in the memory. Besides, we can see that IWEL again showed by light blue color is the best or the second best algorithm in all tests in terms of memory usage. The authors repeated the test, this time on 3 sparse datasets, and WEL again shows the best performance in terms of running time. Also, they repeated the memory test on sparse datasets, and as showed, IWEL is very competitive to line, which is using the least memory and is presented by a very light or white color here. They also run some other tests such as scalability and accuracy tests, and the algorithm shows competitive performance in all cases. I refer you to the original paper if you want to know more about it because of the time. So as the final discussion and conclusion, we can say that the proposed algorithm IWEL is a new efficient algorithm for mining weighted erasable patterns from dynamic or incremental databases. By using a list data structure, the suggested approach can scan a dynamic database which is gradually increasing only once. From the experimental results, we can see that the algorithm shows better performance than the state-of-the-art methods in terms of running time, memory usage, and scalability. As future works, we can say that the techniques proposed in this paper can be applied to various S3 mining fields, for example, a sliding window-based approaches. Also, we can study new definition of the weighted erasable pattern mining. We might come up with some new criteria which are more meaningful or practical than weighted gain value. And finally, we could also consider and study real-life settings in which the significance or weights of the items can change with the time. That's all, and thanks for your attention.